All right, so the next thing that we're going to do is to continue our discussion of the periodic table. And we're going to focus in now on that other piece of information that we can get from any of the periodic table entry. So let's take a look at one of these. Then we'll focus on maybe carbon for right now. So we've already talked about a couple of these things that we see in a typical entry. So in the case of carbon, right? So in the entry here, you have the symbol for the element. So that's C, and then we have the name for it, which is carbon. Remember, if for your elemental symbols, the first letter is always capitalized. If there is a second letter, it's always lowercase. And then we also talked about the number on top, and that there is the atomic number, which is simply the number of protons that we have in it. And then the other number that we're going to see in a typical periodic table entry is the number underneath, which is usually going to be a decimal. And what does that actually mean? So the 12.01 in this case for carbon, this represents a number known as the atomic mass, or sometimes it's called the atomic weight. Sometimes they're used interchangeably, so we'll see either of them when you look in books and online, internet, etc. And what this represents here is average, and specifically, it's a weighted average mass of, in this case, carbon. So it takes into account what are known as isotopes of the elements. We're not going to talk a whole lot about those in our course, but the key thing to note here is what the number actually means. So what it is just an average mass. You can think of it as being the average mass or the average weight of a carbon atom typically, and it's 12.01 for carbon. So remember now, we're looking at the average mass of a carbon atom, so that has to be an extremely small mass. So the unit that we're using here is in atomic mass units, or AMU, right? So it's saying on average, one carbon atom will have a mass of 12.01 atomic mass units, right? That's what that number means for each of the elements. For carbon, it's 12.01. If you look at oxygen, a couple of elements down or across, I'm sorry, you'll see 16. So that means on average, one oxygen atom would have a mass of 16.00 atomic mass units, right? So that's what this last piece of the puzzle means when it comes to the entries in the periodic table. Now, again, the atomic mass unit is a very, very, very small unit of measurement, and it needs to be because this is a single atom that we're looking at in each of these cases, on average, what the masses of each of those are. Now, realistically, okay, in the lab or just working, doing experiments, it is impossible to measure masses of individual atoms just based on the equipment that we have that's readily available. So we need to somehow bridge the gap between the realm of the really tiny. We need to bridge the gap to the amounts that we work with on a regular everyday setting. So we don't deal with individual atoms or individual molecules, but we do deal with amounts of things that we can measure in grams or we can measure in milliliters. So what is the bridge that sort of bridges that divide? Well, we're going to introduce a new term here, a new concept called the mole, so M-O-L-E, and in conjunction with the mole, we're going to talk about a number called Avogadro's number. And both of these two things, the mole and Avogadro's number, you take any chemistry class, it's a big part of any chemistry class. So what does this actually mean? Well, you can think of, first of all, Avogadro's number as just a counting measure or a counting tool that we use in chemistry. That is similar to or analogous to other counting measures that you are probably already used to. So for example, if you think about maybe a pair of shoes, a pair always means two, right? If you have a dozen of something, a dozen eggs, a dozen of something means 12 of that thing. When we talk about a mole of something, one mole of something means always means a certain number of that thing, and that number is Avogadro's number. Of that thing. The only difference now is that this number is not a small number like 2 or 12. It's actually a really, really large number. Okay, and if you think about what we mentioned at the beginning, well, individual atoms of carbon or oxygen or whatever, they are really, really, really small. So you're going to need a lot of them to make up the amounts that you can easily measure out in the laboratory. So when we talk about a mole of something, we are referring to Avogadro's number of that thing, and Avogadro's number is a constant, meaning that it doesn't change, and that number there is 6.02 times 10 to the 23 of something. So if you have a mole of something, you have this many of that thing, whatever that thing is, whether it's atoms, whether it's shoes, whether it's cookies, whatever, it doesn't really matter. A mole of something always represents Avogadro's number of that thing. Avogadro's number, sometimes we abbreviate it, or the symbol for it is N subscript A. That's Avogadro's number. And the mole itself, the word mole, is often abbreviated as MOL. It's not much of an abbreviation, but it's a very common abbreviation that is used. All right, so if I have 1 mole of cookies, for instance, okay, that means I have 6.02 times 10 to the 23 cookies. That's a lot of cookies. Remember, a positive exponent means it's a large number, and then 23 here is a fairly large positive exponent to begin with. So we have a huge number of those things. So you can take that and apply it to a mole of anything. So just like at the beginning, right, we said, it's impossible. It's really difficult to work with individual singular atoms of things. What about now if we had a mole of those atoms? So if I have a mole of, let's say, carbon atoms, guess how many carbon atoms I have? I have Avogadro's number of those carbon atoms, which is 6.02 times 10 to the 23 carbon atoms. And similarly, if I have a mole of whatever, let's say oxygen, insert your favorite atom in here. We have the same number of those atoms, 6.02 times 10 to the 23. In this case, it would be oxygen atoms, right? So a mole of anything is equal to Avogadro's number of that thing. So we can take that, we can apply it to atoms. We can also apply it to even larger things when we start putting atoms together. So for example, we can combine atoms to make larger things called molecules. Okay, and what molecules are atoms, multiple atoms, so more than one, of different elements that are combined in a fixed ratio. Okay, and that definition should sound a little familiar too, because we did talk about compounds, for instance, um, that are made up of multiple elements combined in a fixed ratio. And those are examples of pure substances. Well, a molecule is a subcategory of a compound. So, for example, we have something like water, and you probably know the chemical formula for water is H subscript 2, and then there's an O. So what this means, the way that we interpret the chemical formula for water, okay, the subscripts tell us how many of each of the preceding element or atoms we have in this molecule, right? So this is saying then that if I have one molecule of water, again, molecule is a very, very, very small thing. Now we have, or it's composed of in this case, we have two hydrogen atoms. And when you don't see a subscript after the element, one is understood. So we're going to have one oxygen atom. So a molecule, singular molecule of H2O, has two hydrogen atoms and one oxygen combined in that fixed ratio of 2 to 1, two H's to one O. All right. So again, it's very difficult to work with individual molecules, just like it is very difficult to work with individual atoms. So now, if you think about, if I have a mole of water molecules, H2O molecules, and again, mole and molecules, they kind of look similar, because mole is part of the name, but they're different things, right? A mole is a counting measure. A molecule is actually a collection of atoms combined together. So if I have a mole of water molecules, guess what? I have the same number, Avogadro's number, of those molecules. That's a lot of water molecules. Right? 6.02 times 10 to the 23. And if you were to write that number out, by the way, so 602, and then you would have 21 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. This is the actual number that 6.02 times 10 to the 23 refers to. So if you have a mole of water molecules, right? That's how many water molecules you have. It's a large number of water molecules, but because the molecules are so small to begin with, it actually doesn't amount to a whole lot. So a mole of water molecules really is only about equal to, so approximately equal to about 18 milliliters, which is not a whole lot. That's just a small gulp of water. And that's how many water molecules you're actually drinking if you drink about 18 milliliters of water. If you're drinking Avogadro's number of water molecules, right? So knowing what a mole is important because we're going to use this here in a second. Avogadro's number is how we sort of bridge the gap from the realm of the really tiny individual atoms, individual molecules, to the realm that we work with, grams, milliliters, etc. So how does this then tie back into the periodic table? Well, we're going to take a look at that in the next section. Okay, so let's take a look at how we can do a couple of these or incorporate a couple of these things in some calculations. So let's say that we had a sample of We'll use carbon again. So a sample of carbon has or contains 3.5 moles of carbon atoms. Okay, how many carbon atoms are there in that sample? All right, so here we're given moles of C. We want to convert that to number of carbon atoms. So now listing what you're given, what you need should hopefully help us figure out that what we're going to need to use in this case. So we're going to have to use Avogadro's number to convert from moles to number of those things, right? So Avogadro's number relationship, 1 mole of anything. In this case, it's 1 mole of carbon atoms will be equal to 6.02 times 10 to the 23 carbon atoms. So that's our relationship. That's our equality. We can take that, make it into any conversion factor that we want. So we're given here, we'll always start with what's given. So we have 3.5 moles of carbon atoms. Right? If you want to get to number of atoms, you're going to put that unit on top. So we have 6.02 times 10 to the 23 carbon atoms. And that's for every 1 mole of carbon atoms. So now my unit of moles of carbon atoms cancel. I end up with actual number of atoms on top. So the units make sense. And then I end up just multiplying the 3.5 by the 6.02 times 10 to the 23. So what do we have? It's 3.5 times 6.02. All right, so that's going to give 2. What do we have here? 1. 2 sig figs, and then that's times 10 to the 24, and that will be carbon atoms as the unit. Now, a fairly straightforward type of calculation, but you want to make sure that you check your answer in terms of the size of the number. So if whenever you're calculating the number of atoms or the number of molecules of something, you should be getting a fairly large value, right? So your exponent here should be a big positive number. And then in this case, the units also work out well. Let's take a look at another example, maybe going in the opposite direction. So let's say now a sample of water. So H2O contains 3.65 times 10 to the 25 water molecules. And we need to figure out how many moles of water molecules are present. Okay, so now what are we given? We're given number of water molecules. And we want to convert that to number of moles water molecules. So again, the relationship between number of something and moles of that thing, we're going to use Avogadro's Avogadro's relationship. And again, that is the same relationship if I have 1 mole of anything. In this case, it's water molecules is equal to Avogadro's number 6.02 times 10 to the 23. Water molecules. So, whoops, that's my relationship, very similar to the one before, except now we're looking at water molecules rather than carbon atoms. What did we start with? What was given to us at the beginning? We have 3.65 times 10 to the 25. And then this is water molecules. So I'll just write the formula, water molecule. So we're starting with that. And now we're going to take our equality here, stick it in as a conversion factor. I want to end up with moles as my unit. So I'm going to put the moles side of this on top. So for every 1 mole of H2O molecules, I have Avogadro's number 6.02 times 10 to the 23. So the number of water molecules go away, and I end up with moles as my units, so that the units make sense. And then I'm just dividing now 3.65 by times 10 to 25 divided by 6.02 times 10 to the 23. All right, so we have 3.65 times 10 to the 25. And that is divided by 6.02 times 10 to the 23. And that should give 60.6, so 3 sig figs. And then that's moles of H2O molecules. Okay, and again, the units make sense because that's the only unit we're left with. The number makes sense. Usually you find moles of things. It's a much smaller number relative to the number of actual molecules, really tiny things that we have. So the point here is we can use Avogadro's relationship to convert between number of moles of things and number of individual particles, whether those particles are atoms or whether they are molecules.